ATX. What is ATX? ATX. Oh, good, good. Any confusion? Good, good. Great handwriting. Oh, great, great. Whoops. Did you study a bit?
A little bit.
Oh, okay. Well, good. See, if you get this xt x and xty, just simple matrix multiplication. And then to find the beta, you can either use augmented matrix or you can find the inverse. Oh, you're right. Ready? You're fine. Yeah. Alright, did you get towards it? Jella, you got it? Okay, good. There's the unit. Yeah, the word is not that clean, but this. Yeah, yeah.
Actually, if we had nerves, If we have this, can we do this?
Seems like all of you have idea how to solve this. Okay, good. Now I'll move on, guys. If you didn't finish, finish home by yourself. Then let's say you got the slope. Let's say you got the betas, right? The intercept and slope. If I ask you to estimate the point when x is 4, what would you do?
Plug in 4.
Yeah. So that was the next part. You simply plug in the value 4, 6, if I ask 4 or 6. Okay, I'll not ask more than second degree. So linear least square will be the exam topic. I'll not ask other topics. Okay, so finale of this semester, chapter 7.1. Okay, so this. Okay, let's try this together. Okay. For this question, either I make the matrix simple so that you can just find out the eigenvalues, or I'll give you the eigenvector at the beginning, but not normalized. Let's say I give you this 3 eigenvectors and pairs of 3 pairs of eigenvector and eigenvalues. Diagonalize. Find it there. But specifically, diagonalize after you normalize each eigenvectors. Okay? You have to normalize. Normalize. if I ask you just write out the inverse of the P, whatever you have, what do you have to do?
The transpose.
Yes, yes, whatever you have, whatever you have.
So
So depending on the order of the eigenvalue, you may have different P's. Okay? Do you make sense?
Unless they're the same.
I don't know. Okay.
Right?
Okay.
Yeah.
That's so much easier.
Oh, okay. Okay, what is the meaning of normalize? So let's say
Make
this.
it one, just one of them.
Just forget about the other thing. Let's look at this vector. Okay. What is the length of this? Right. Length of this vector. Square root.
Square root 2.
Yeah, square root 2. Right? Because you square every one, you square 1. Right? You add them all. Square root. So you get square root 2 for the length. So you just divide the original vector by its length. And that is just normal. Okay. Now I want to repeat the same process for the other two vectors. What is the length of this? Yeah, square root 6, so you just multiply, divide by square root 6, and this is all the square root 6. Okay? And then originally there, the name of this vector was v1, but I'm gonna just call v prime because I normalize it. So I'm gonna name with different
Because once you get rid of that,
term.
you have.
So it's gonna be v1 prime or v2 prime v3 because I normalize it. Okay? So once you normalize this, it's the same process as the last example, last problem of exam 2. You have eigenvalues, right? And you also have corresponding eigenvectors. How do you construct the? Just copy paste these eigenvalues on the main diagonal line. So D should be what? Yeah, let's follow this order A63. A63. I just simply copy paste on the main diagonal line. Okay? And then zero, all zeros. And then for P, right? P, you also copy paste this normalized eigenvector because I want you to find I want you to diagonalize this matrix using orthonormal columns, which are these normalized columns. Or are they orthogonal? Are they orthogonal? Yeah. Do we have to check? Are they orthogonal at the beginning? Yeah, they are. Right? Okay. So we didn't have to check. If one of them is, I think the next example is one of them is not orthogonal, then in that case we have to use what? Yes, to make orthogonal basis. But anyway, so we already got at the beginning we already got orthogonal eigenvectors, but we didn't find normalized vectors, so we normalized this. Therefore, we have orthonormal columns at this point. And then P is simply copy and paste, right? You copy and paste this following the order of eigenvalues. So it's going to be negative 1 over 0, 2, 1, 0, 2, 0, and 1. Yeah, something like that. I don't know. You just a little copy paste. Okay? And then once you construct P inverse is just transpose. Okay? But let's say for some reason you just write instead of 8, 6, let's say you swap the order of first two eigenvalues. Let's say you got 6, 8. Then just copy this eigenvector first, right? And then for the second column, you just copy this eigenvector. in that case, you may have different P, but that is okay. I just want to find P and D, and then I want you to find the inverse of P, whatever you have, based on whatever you have for P. Okay. Any question? So let's see if okay. So this question. Okay. I may be asking this question asks you everything. Okay. So I give you a characteristic equation. I didn't say eigenvalues explicitly, but what are the eigenvalues? Yeah, 7, -2. We have multiplicity 2 for eigenvalue 7. And then, let's say I gave you eigenvector. One, just a eigenvector. They're not normalized. Are they orthogonal? Yeah, almost. Meaning one of them is not orthogonal. What? Which one? Which pair is it? So if I try to compare these two, are they orthogonal? No. So what about V1 and V3? They're orthogonal, right? Okay. Do you guys know how to figure out which if two vectors are orthogonal? How do you use?
Dot product.
Yes. Okay. Dot product should be 0 to see if you to say two vectors are orthogonal. What about these two? Orthogonal?
Yep.
So even though these first two vectors, eigenvectors, are not orthogonal, I still want you to find P inverse using orthonormal columns. Okay. Orthogonally or diagonalized matrix means this means use orthonormal columns to construct P. So it's yeah. P is orthogonal. Oh yeah. It'll be messy, but orthonormal basis might be useful. I think I saw some definition. Sorry. I don't want to waste you. But orthogonal diagonalized means use orthonormal basis. Okay, but in the exam question I'll explicitly say use orthonormal columns to construct P inverse. Anyway, so how do we make this orthogonal? This way. Yes. Okay. Then what should we do? What should we do, guys? Should I use? Okay, there are two ways. I use Gram-Schmidt based on these two, or based on these three. Which one would be easier?
Just the two.
Yeah, just two. Yes. Okay, let's use Gram-Schmidt. Guys, compute. See if you can guess. Okay, guys, did you get it? This,
Hopefully. So the first two.
did you get this?
Yes.
Okay. And then, what was the next step? So you got orthogonal bases. Yes, 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 yes. We have to normalize. Yeah, okay. So don't forget normalize. The first vector is, what is the length of this? Square root 2. So you divide square root 2. And after you get the second vector from geometric process, you get the length of this, and there will be square root 18. No. I think it's not square root 18, but.
We can scale those up to get rid of the fraction.
Yes. Thank you. So we can scale this by 4, multiplying every entry by 4, and then you can get the length of that and divide it this by each angle length. So that will be square root 18. And what about third vector? And you simply get the length and then normalize it. So let's say you got 3 vectors. Normalize also orthogonalize 3 vectors. Okay? How do you find P? Then, if I ask you, find the inverse of P, what is it? Yes. Okay, so great. Don't worry about this. Next chapter, quadratic form. Okay, maybe just simple question. I give you this. If I ask you to find the matrix to make a matrix X and A, so that you can get this. Construct A. What are the X and A? Guys, remember last? Just quickly review. If I multiply xt a x, then we get 4 times x1 times x1 here. Then 0 times x1 times x2. So if you guys remember, you got the pattern, some like pattern like this. You literally copy paste 3 and 7 or the entries on the main diagonal, and those are used for the square terms, such as x1 square or x2 square. But these terms are used for the x1 times x2. Then you have to add this to make the coefficient of x1 times x2. Okay. So if I do backward, what A should be. Main diagonal, 5, 3, 2, right? And then, so now, a little bit confusing part is, so 5, 3, 2, and then, what about here? So you see, 1, 2, right? Means first row, second column, or first column, second column. You're gonna take half of this, so therefore you're going to have -1, half, -1, half. How about this? First column and first row, third column, or your first column, third row. Because we don't have the term multiplied with x1 and x2. 0, 0. What about next? Half of this. 8. this should be A. If I ask you to write out the answer, you should write like this. x1, x2, x3. Why do we have 3 variables? Because it's 3 by 3. If I ask you 2 by 2, then you should write x1, x2. Okay, one more thing. If I increase the size, so let's say I have a term. On top of this, let's say I have 7x 4 powers 2. Then I have 4-dimensional space. What A should be, what X should be. Everything's same, just add one term, and then I change the dimension. What A should be.
It should be a 4 by 4, right?
A should be 4 by 4, and then based on what we have, what should I add here?
That's at the bottom of the diagonal.
And then everything else here, right? Because I don't have any term term that has more than 2 variables, also containing. I don't have the term that has 2 variables and containing also x4, right? Because I just added this term, which goes here. But if I add, let's say 11 x1 x4, which part changes? If I add this, yes, first row, 4th column, or 4th row, right? Or 4th row,
First one.
first column. Yeah. Oh, thank you. Sometimes my brain doesn't. Okay, so here, change this. 11 over 2. 11 over 2. Okay. Okay, let's try this. I want you to diagonalize this. And in this case, you have to figure out the eigenvalues by yourself. Okay, let me ask. Would you rather have 2 by 2 and you have to figure out eigenvalue and eigenvector by yourself? Or would you rather have 3 by 3, already eigenvalues are figured out?
2 by 2.
2 by 2?
Yeah. Why would you just give us the eigenvalues and vectors? For like
4
4
by
by 4.
4 by
Yeah.
4, you give us
Whoa, whoa.
nothing.
Yeah, 4 by 4, you give us the eigenvalues.
4 by 4, you give us nothing.
Whoa.
4 by 4, everything is given?
4 by 4,
no more
nothing is
specifics.
given.
Oh, okay.
Yeah. 5 by 5, here we have.
Whoa, no.
And there's 2 power of 2 multiplicities.
Billion by billion matrix.
Netflix, Richard.
Actually, I was watching it.
What were you watching on Netflix?
Oh, Matrix.
Oh, the Matrix.
Oh, yeah, because that was my first time watching it. Oh my god, this teaching linear algebra, what a coincidence. I finished all of it. Matrix? Matrix. All of them, I watched all of them. Also, I recommend K-dramas, because I'm pretty. Oh yeah. I love that show.
So, yeah. I've only seen the first season. It's so good.
Oh yeah.
What is it?
Physical endurance, like
Not all Koreans are not that fit.
bodybuilding type of shit.
Oh, physical
like challenges.
100, yeah, it is, it is.
Or is that the Korean one?
Yeah, it's the Korean one. Yeah, they're looking at that.
Just like you. We should go with this 100.
Okay, so let me ask. Would you rather have the problem like this? So I'm thinking, I'm trying to make the exam a bit easier. Okay. So for this example, the vectors are given, but these two are not orthogonal. They're not orthogonal, right? But to find out the orthogonal vector, we use Gramsci. Right? So if I ask this question, I don't need to ask. I feel like I don't have to ask a question regarding Gramsci.
Yeah.
So would you rather have this instead? So it's 3 by 3. I don't prefer, but is it okay if I ask this question because it involves Gramsci and I don't ask Gramsci?
Gramsci's pretty good.
Very good.
I rock with it.
Okay. Then, it's kind of repetitive.
But if you can have both questions.
No, I'm trying. I may ask.
That would be one massive question that does everything.
Okay.
No.
Okay, then in that case, then you have to figure out from I can remember. That is one question.
And then you use the eigenvectors to do a linear approximation.
Linear approximation.
No, preferably no linear approximation.
Only simple game, please.
Or any type of line of best fit approximation.
Okay. You gave me such a good idea. Okay, so yeah. Actually, I'm going to do it. So.
I like it, yeah. I like it.
Okay. Thank you.
You're welcome. You should give me bonus points.
Okay. Where was it? Yes. Okay, so. Okay, I'll make a question of it. Okay. Once you, that involves many concepts as much as possible.
No, he was kidding.
Wait,
He was
wait.
kidding.
Really?
Don't do that, wait.
Okay.
Something like a bonus question.
Yeah, bonus question.
Yeah.
If you want extra credit, I can give you.
Oh.
Right now, like for example, like.
So you put it on the final?
I mean, right now, like, if you wanna explain how things going right now, like, can you explain everything? Then I'll give you extra credit.
On the final?
I mean, like, explain homework. I cannot give you extra credit on the final.
You could give us a bonus question on the final. Maybe like one uber hard question at the end if you have extra time.
That uses like all the stuff. Yeah.
But like not that hard.
Well, like make it worth 10 points extra credit on the final. Like give us a proof. Prove that this works.
I'll think about it.
And I'm thankful for it, but also I kind of like proof.
You like proof?
He likes proof.
No,
I didn't
he
say I
likes
like
proof.
proof. He likes proof.
All of us.
No, it's just him.
Okay, who wanna explain this? 10 points extra credit to your homework 1.2. Just pretend just pretend to be me here to explain this. If you want extra credit, I think you
10 points extra credit if you explain like questions.
Yeah, explain questions.
Explain the process and actual.
Yeah, everything like just act like a professor right now. Yeah? No one?
I think Tomas is reviewing it right now, but I think he's getting ready to explain it.
Okay. Dr. Thomas, come here.
Hey.
So from the beginning of
Yeah. So,
you're gonna help me a little bit because
yeah,
I'm not very sure.
Of course.
Okay.
We will be asking questions.
There's the English that I'm not very sure on.
Yeah.
Language of this.
My English is
Okay. So there exists a scalar
Mhm.
lambda where there exists a scalar lambda where like there's some span.
Uh-huh. Oh, good.
Yeah.
Okay, good.
And then
So that'll be eigenspace and then
eigenspace, right? And then the resulting.
So we want to find eigenvalue, right? Did you find eigenvalue? Did you find eigenvalue?
Yeah. Well, I think I got numbers -7 and 3.
Yes. How did you find it? Copy paste?
Copy paste.
Oh, from here?
No,
Or-
no.
Oh. How did you?
That'll be a racing word.
To solve for lambda,
Uh-huh.
we subtract it from both sides. Well, it will end up being equal to 0.
Yes.
And then we are able to make it in the form of ax equal to b, or 0 in this case.
Yes,
So
yes.
then we take out x. That makes it a minus lambda times x. So this is a, or this a,
Uh-huh.
from what we normally do, that equals 0.
Okay, good.
Dr. Tomas, how can we subtract a scalar from a matrix?
That's a great question.
Okay,
Wonderful
you
question.
deserve 10 points. Okay,
Great question.
Okay.
Well, it turns out that a scalar, you can rewrite a scalar as a scaled identity matrix.
Uh-huh.
And that way, so lambda times the identity matrix, and now they're both in the same form, they're both in
Mhm.
M by M matrix, and you can subtract.
Okay, good.
Yeah. So that's going to be lambda,
Can you show the process of getting the lambdas?
in the lambdas?
Yeah, the exact values.
Check. Okay. So then here's our A. Ooh, can anyone see this?
Yeah,
Oh, yeah,
we're
yeah.
good, we're good.
Great.
Okay.
Great.
So we got, what is that?
1.
1, -4, -5.
Yes.
And then we want to find the determinant equal to 0, which is why I wanted to ask you why specifically we said, I can't remember why we said the determinant equal to 0. But regardless,
Oh.
we subtract this from that lambda identity matrix,
Okay, good.
which results in a new matrix, 1 minus lambda. On the main diagonal, we have subtract by lambda.
Oh, great.
And now we can find the determinant
Yes.
set equal to 0.
The reason of finding the determinant is find the characteristic function, characteristic equation. And when that becomes 0, those are the eigenvalues. Yes, great. Okay, Dr. Thomas, how you doing? Good.
-5, that's an S.
Minus 5.
5, that's not technically 5.
It's okay.
-5, negative lambda, plus, yes, because that's how math works. That's another S.
Uh-huh. Plus 5 is
And then
plus.
lambda squared minus 16. And remember, we set it equal to 0.
Yes.
Now we can rearrange lambda squared plus 4 lambda minus 21.
Yes.
And now lambda plus 7 lambda minus 3.
Okay, great. And that becomes 0 when lambda is 3 and -7. Therefore, the eigenvalues are
3 and -7.
okay. So based on that, let's skip the process. Like let's say you got the eigenvector. Just show how to find eigenvector corresponding to 3. So now we want to find the eigenvector corresponding to lambda 3.
You guys remember this matrix right here?
Mhm.
Lambda. We just plug in each lambda each time.
Yes.
And set it equal to 0 because originally we had set this equal to 0.
Uh-huh.
It's like that.
Uh-huh.
Yeah. So we find the null space.
Yes. Great.
So
No space.
we can do
3.
3? Okay. 1 minus 3.
Great.
-5 minus 3, -8.
Uh-huh. Okay.
Then
Augmented matrix 0, 0. Okay. Finding no space.
we can reduce these both by 2 to make our lives easier. Negative 1, negative 2.
And then there's also scale
Oh.
by 1. I mean, scale to 1.
Yeah.
Yeah.
Right, and this is also 1, 2. Okay.
Yes, yes.
2. Then we subtract R1 by R2 or vice versa. Get 0.
Yes, great.
Then, sorry, minus 2, x2 equal to 0.
Uh-huh.
Rearrange, we get x1 is equal to negative 2x2.
Okay, good.
Yeah. And then that ends up being, so we can take the scalar x2 out.
Mm-hmm.
We have x1 scaled x2 by 2. X2 is just itself,
Mhm.
and this is a 2 by 2 matrix, so that's not anymore.
Yes, great. So that is eigenspace. Whatever value you pick for x2, you can make an eigenvector. There's so many eigenvectors. In this case, the author picked minus 1 over square root 5. But okay, good. So what value do you want to pick for the eigenvector? Yeah. Pick the eigenvector. Yeah, eigenvector. You have to find a eigenvector, one eigenvector, because we want to find p. P.
Oh, what?
What p? So we want to find we want to diagonalize, right?
Oh, you mean that we just do another?
No. So this is.
Oh, we can choose one or normalize it.
Yes. You can choose one and then normalize it. That will be this. I mean, scale of this. Okay. So okay, Thomas, thank you. Okay, so anyway, so you keep this, you repeat this process, you find another eigenvalue and normalize this, and then this too. And based on this, you can find P and D, right? Okay? I wanna ask this change of variables, but okay, so almost done. Okay, let's do one last problem, and let's call it it now. Okay, this one we did together. Diagonalize, meaning find P and D using orthonormal basis, orthonormal columns. Right? Okay. Maybe not this one. Okay. Okay, thank you. What's it?
Matrices are orthogonal. It is. It's orthogonal. If orthogonal, find the inverse.
I think this one. Yeah, let's give it a shot. I don't know the answer yet, but let's try this.
Diagonalizing it?
Yeah, find the eigenvalue first. Let's see. I don't think we have enough time for all of this, but find the eigenvalue and find the eigenvector. And then what was the first thing? Yeah, normalize. Let's see what eigenvalue. Eigenvalues are quite special. One second. quite messy. I just calculated it. Sorry guys, that was quite messy. Let's try this. It's quite simple. What is the eigenvalue of this?
4 and 3.
Yes. Based on that, find the eigenvector. Oh, good. Great. Yeah, so find P. P, D, yeah, I'll make sure I'll post a review regarding true false tonight.
We have a
Sorry.
problem like this.
Oh, what?
Do we have one like this?
Oh, is it?
Specifically.
Just that, like this one.
No, I don't like this.
Like word for word,
Bar
bar
for
for bar.
I don't like this one.
This is great.
I'd rather do
What did you figure out? Okay. So what is P inverse?
The transpose.
But still identity, right? So basically what you did is I, D, I. P, D, P inverse, but essentially this is 1, 0, 0, 1, and then 4, 3, 0, 0. And that is 1, 1, 0, 0, 1. What is this? You're multiplying the original matrix by identity matrices. That's why you get the same. But anyway, it's a good practice. Good practice. Okay, see you tomorrow. Okay, last class tomorrow. If you, I want to take picture if you don't mind.